This slide, what we're talking about here is we have a perpendicularity tolerance here applied using two planar datum features. Okay, in this case we have datum A, which is the lower surface. We have datum B, which is the far surface. And then what we have here is this end surface here, this surface, now has a perpendicularity tolerance to both A and B. Okay, so essentially what we're doing is we're using two datums to establish our planes for our perpendicularity tolerance. So how would we verify this? Okay, this is a lot like the last slide, but what we've done here is we have this block right here. This is datum A simulator. And then we also have a datum B simulator here too. Okay, we have datum A and datum B simulators. We have our part clamped such that the part is flush up against our datum A simulator and flushed up against our datum B simulator. And then we run our indicator over top of the part and make sure that the perpendicularity is not out by more than 5 thousandths. So that's the difference between a one datum and a two datum. Okay, so if we compare this slide with the one datum slide, what we have here is this is the one datum. We don't have the simulator picking up datum B. Okay, so when we jump over to this slide here, we have datum B, and then we have a simulator picking up datum B surface. That is the difference between one datum and two datum. Let's talk about perpendicularity to a facial surface elements on a shaft. Okay, so what we have here is we have a cylindrical element, we have a surface at the end of it, and it has a perpendicularity tolerance within 7. No modifiers needed here, and then the regardless of material boundaries assumed. Again, that is rule 2 of GDT. What does this mean here? Okay, so what we have is we have a 7 thousandths between two perpendicular planes, two planes perpendicular to datum axis A. That's what that means. Okay, so perpendicularity of 7 thousandths with A. So perpendicularity applied to a feature of size. That establishes the control of an axis or a center plane of the feature, and it may be defined as control within the virtual condition. Feature control frames must be associated with the size dimension. Okay, we need to establish that the feature control is applied to a feature of size. And it may be adjacent to dimension, or it may be attached to the dimension line. We've seen that before, where we attach a tolerance to a dimension line. Okay, so here we got perpendicularity of an axis interpretation. Okay, so what we have here, we have the perpendicularity tolerance applied to the dimension lines. That means that this perpendicularity tolerance is applied to a feature of size. Or the other way to do it is to put the geometric tolerances right next to the feature of size. That's the other way to do it. Now, what does this mean? Okay, so this one we're using a MMC modifier here. It's giving us a virtual condition. Okay, so we have 375 plus or minus 2. Our virtual condition would be our maximum size. Again, this is an external feature, so our maximum size is 377 plus, okay, since we're talking an external feature, we're going to add the 6 thousandths to get to our virtual condition. So our virtual condition here is 383. That's what that means. Okay, so if our pin size comes in at MMC, we got 6 thousandths allowable perpendicularity tolerance. If our pin size comes in smaller than MMC, for each thousandth that comes in smaller, we get another allowable perpendicularity tolerance in thousandths. Okay, so our least material condition is 373, in which case we pick up 10 thousandths perpendicularity tolerance. So again, this is a virtual condition, allows our parts to fit. So essentially, as we deviate from the maximum size, we get more room for our perpendicularity tolerance to vary more. So that's what it means when we apply these tolerances with a maximum material condition modifier. Now, how do we verify one of these? Okay, we verify with a functional gauge. Okay, so the functional gauge will pick up datum A. Okay, so if we look at what we have here, we have datum A here, and then we have a virtual condition of 383. So how is our functional gauge built? It's built with a datum simulator here to pick up datum A, and it's built at the virtual condition of the shaft, which is 383. So as long as I can take my gauge, my functional gauge, apply it over the part, and it fits over this pin at the virtual condition, and it contacts datum A at 3 points, then the part is good. So this is how we use a functional gauge to check the virtual condition, used to check the MMC size plus form tolerances. That's how we do that. Okay, perpendicularity hole applied at MMC interpretation. Okay, so what we have here is, the last one we did was a shaft, now we're looking at a hole. Okay, so we have this part here, we have datum A, and then we have this hole, 392 plus 6 minus 1, with an 8 thousandths perpendicularity tolerance at MMC. So the first thing we do is we calculate what our virtual condition is. So our virtual condition is the minimum hole minus the perpendicularity tolerance. So what we have here is 383. And what does this mean? Is we have our datum A right here, and then we have this 383. As long as that 383 fits in there, that gives us our 8,000 cylindrical zone when the feature is at MMC. So that's what that means. How do we verify this? Again, since we're using MMC modifiers, we can verify this with a functional gauge. A functional gauge is essentially a block with a hole put in it at the virtual condition. And the block has a simulator for datum A right here. So as long as I can take my gauge right here and it fits in the workpiece, by fitting in the workpiece, I mean the pin in the gauge clears the hole and contacts the simulator for datum A, as long as I can do those two conditions, I have a good part. So that's how a functional gauge is used to check the perpendicularity of a hole. Okay, controlling one cylinder perpendicular to another. When we do that, no diameter symbol is used in the feature control frame. The orientation tolerance does not control location of one hole relative to the datum axis. It only controls orientation, and the position tolerance would be required if you wanted to control the hole orientation. Okay, so here's what we got. Controlling one cylinder perpendicular to another. What we have here is we have a bar, a cylindrical, round cylindrical bar. We have a hole drilled through that bar. Okay, the hole has a diameter of 188 thousandths plus or minus 2, and then it has a perpendicularity tolerance of 7 thousandths at maximum material condition. So what does that mean? That means that I have a 7 thousandths perpendicularity tolerance, and then two planes perpendicular to datum A, and then the center axis of my hole must fall within those two planes. Notice that there's no diametrical symbol here, in which case that this becomes just two planes for a tolerance zone. Here's controlling perpendicularity of a center plane. Okay, I have an 8 thousandths between planes perpendicular to datum A. And then I have another condition over here that shows you what that is. I'm going to stop this here and finish in the next